until, and I'm sorry, but I usually do show my ignorance. Until 2 years ago or so, I didn't even know things like decadals existed. I was deep down in the bowels of making things happen. And I didn't know a whole lot about that level of deliberations and decisions and recommendations. So this has really been a very educational and entertaining setup going through and putting together this program. I'm very happy it's working this way. Next session, the science pillars from the Astro Decadal. And our moderator for this session is Robert Petry, the Director, Astrophysics Science Division, Astro Goddard. Welcome, Robert.
So all of us are very excited about the program that we heard about a few minutes ago that the Decadal has put forward regarding particularly machines. And that tends to be the thing that we focus in on. What are the programs? What are the things we're going to build over the next 10 or 20 years? But underlying that, the key to all of this, of course, is the science and the big science questions that the Decadal has put before us. This group is going to explore some of those questions. We've asked each of them to talk about the science in the Decadal survey report that excites them the most. And rather than me introduce them, I was going to ask the panelists to introduce themselves, and then I'll come back and say how we're going to format this particular session. So why don't we start at the end with Erin?
All right, my name is Erin Smith. I work at Goddard Space Flight Center, and I'm the Deputy Observatory Project Scientist for JWST. And my science is, I look at a particular kind of dust. It's polycyclic aromatic hydrocarbons, so PHs. They're basically benzene rings that kind of make these assemblies of things that are not quite molecules and not quite dust. But we see them everywhere. We see them in planetary nebulae, evolved solar type stars. We also see them in star forming regions. And more recently, they've been used to trace star formation throughout the history of the universe. And so that's kind of my science case. It's kind of a cool way to be able to look at what happens in the dark places between stars. Because this dust exists, we think it gets created in these carbon stars, and then it's just not lit up by UV anymore. And so it sort of sits and waits, gets processed in the interstellar medium, and then it gets lit up by UV in star forming regions. And so we can find out what happened in those sort of mystery times in between the formation of this dust and when it gets incorporated into new planetary and stellar systems.
And I'm Shawn Domagal-Goldman. I'm at NASA Goddard Space Flight Center. And my science is exoplanet biosignatures. It is, how are we going to look for signs of life on these planets around other stars? And the team we work with addresses everything from what makes a good biosignature. How will we recognize life when we see it? How will we not get tricked by nature by throwing us a planet that may have some biosignatures even without life, or we think are biosignatures even if the planet doesn't have life, or the opposite. How will we recognize life when we see it if it exists on a truly alien world that where life presents itself in a way that's very different from the way it presents itself on Earth? So we work on that stuff, and then I also had the honor really and the pleasure to work on the study concept teams that led into the Decadal survey. I was Aki Roberge's the deputy study scientist for the LUVOIR study concept. And I was also working with our JPL colleagues on the HABEC study concept. And those were the missions that led to the recommended UV-OIR direct imaging flagship mission out of the Decadal survey. And that's exciting to me, both because I genuinely love those teams, but also we're basically at the point now where the idea of life on planets around other stars, it's not just something we talk about at a coffee break or at a pub or philosophize about. It's something we can apply the scientific method to. And that means designing specific experiments and having the partners and the engineering and programmatic capability to build those experiments. And that's why this morning was so exciting to me. It's why the Decadal survey was so exciting to me. And it's why I'm really excited for everything that's coming next. So yeah.
Good afternoon. My name is Marc Postman. I'm an astronomer at the Space Telescope Science Institute, and my area of expertise is galaxies and large-scale structure in the universe. And I came to Space Telescope Science Institute about 8 months before they launched Hubble. And so that was an exciting time, which quickly turned into a terrifying, sad time when we found a problem with the mirror. So I'm very happy to see that that experience is not being repeated for James Webb. I'm so excited about not only the potential that James Webb has for my particular area of studying galaxy evolution, because it's going to absolutely revolutionize that, but looking forward into the next decade and what Astro 2020 has recommended, in particular, the array of advanced UV optical, a very large UV optical telescope, which is going to allow us to see star-forming regions that are only a few hundred light years across in any galaxy at any redshift. That is an amazing capability. But we have to couple it with other wavelengths. Modern astrophysics is not done with just one wavelength. So we really need that complement of X-ray and mid and far infrared as well, and as well as advanced radio from the ground. And all of those in the Decadal are being proposed. There's key advances in all of them. So I'm really looking forward to that.
Hi, my name is Suvi Gezari. I'm also from Space Telescope Science Institute. And my area of interest is time domain and multi-messenger astrophysics. So I was very pleased to read the steering committee's recommendations for a priority in new windows on the dynamic universe. And I also had the pleasure of being a part of the Astro 2020 decadal process by being on the optical and infrared ground-based telescope panel. But we'll be talking about various exciting breakthroughs in science from the decadal in this panel. But from my area of interest, we truly are in an era of discovery, and I'm really excited about the future potential from space.
So thank you for those introductions. So the way we're going to do this particular panel is I have a small number of questions I'm going to ask the panelists to address. And then we're going to open it up to the floor so that you folks can have an opportunity to ask the panelists. As you can see, we have a wide range of scientific expertise up here. We can't cover the full range of astrophysics. That would take a room full of people. But at least in some of the key areas that were covered by the decadal, we have the right people sitting here. So I guess the first question for each of you is, all of you had something very exciting, relevant to your direct field of study that came from a decadal. What in the decadal excited you that it is not in your field? What was the thing that really stood out to you about the decadal in terms of the scientific goals that were set out?
Suvi, do you want to go first this time? No? Okay.
You go.
Okay. So this one's, I've got a different hat I wear, which is I'm in charge of a group that builds spectrographs for solar system science. So there's two things that are exciting to me that are related. One is the amount of data and spectroscopy that we could do inside the solar system with these new great observatories, because they could do fantastic planetary astronomy. So some of the simulations we were making in advance of the decadal survey had flyby quality data in terms of the imaging you'd get of other worlds, not to mention the spectral data you'd get that would help you understand, how planets work, how atmospheres evolve, and in great detail inside the solar system. And then to combine that with the spectra we're going to start getting with Webb soon on exoplanets on those same kinds of questions, that we could continue through the future with these next new great observatories, we'd really be able to understand better. The question I've heard it put is like, are we Portland, right? Like, is Earth in the solar system, is it weird? Is it like wonderfully weird? Or is everything kind of like our home? And I really look forward to like those kinds of questions.
So I really enjoyed reading about multi-messenger astronomy. I think that that's an area that is just so exciting, and we learn so much about the universe. And it's fun to think about science that uses a completely different messenger, right? So we're not just talking about taking photons anymore. We literally are looking at the vibrations of the universe, and there's something very fundamentally exciting about that. And so it was, I liked reading about that. And just in general, I really liked how the Decadal emphasized these synergies between very disparate groups. And I know that part of that was the large mission studies really leaned into that. But, it's not just one community that gets things. It really was, this is how we do the science that touches on multiple points. So I think that was two, but yeah.
Well, for me, I spend my days at Redshift 1 and beyond. But the thing not in my field that is most exciting to me is the ability to answer the question, are we alone in the universe? I mean, this is a thing humankind has been asking for millennia. And we're now at the point where we have the technology and the scientific knowledge to actually do the experiment. And I think that the fact that the Decadal put its blessing and said, go forward and let's do this, is the thing outside of my field that I found was really the most exciting.
So I'm going to cheat and stay in my field because it's so exciting. But the thing that I really appreciated from rereading through the Decadal report was that the most exciting breakthroughs in transient and multi-messenger astrophysics relied on the coordination and sort of co-discovery by multiple telescopes operating on the ground and in space, covering different wavelengths, particles, having wide fields of view, narrow fields of view, sensitivity, rapid response. Basically, no one stood alone in these discoveries. While the neutron star merger was detected in gravitational waves, what made it so dynamic and exciting was the co-detection in gamma rays and optical light and infrared and X-rays and radio and on and on. So it showed that these communities that come from various different parts of astrophysics, from the physicists running LIGO to the astronomers pointing at patches of the sky, looking for kilonovae. These communities need to work together, coordinate, and communicate. So the thing that I took away is that we really need to think in the future of having a healthy ecosystem where these different experiments and different communities are able to communicate efficiently and rapidly with each other and to use their telescopes and facilities in coordination.
Okay, thanks. So as we've talked about, the Decadal has put forward a very bold vision of what we should be doing over the next 10 or 20 years. I want to pull the focus back to the nearer term. What are the things we can be doing now in terms of precursor science that we can do with current facilities that will allow us to make the best use of these and help us better design these future facilities?
Okay, I'll go first this time. There's been some discussion of the role of data and big data in this current era. So one sort of precursor activity would be to get the infrastructure ready for combining these major data sets and cross-correlating them and doing inferences on them at the same time, pixel level analysis or catalog level analysis, but basically developing the data cyber infrastructure to be ready to pounce on the next big discovery.
I think one of the big challenges, especially if you look at the capability of the very large ground-based telescopes, the 30-meter class things, as well as the flagships that are being proposed, 10-meter class or 6-meter class UV optical, advanced X-ray telescopes that would see the very first black holes, is we need to be able to prepare to interpret the data that those facilities are going to deliver, and simulations are an excellent way to do that. The issue I see is that right now there are the people who are the experts in making those simulations, but the ability to access the simulations by the broader community is still something that's somewhat limited. So having data archives that archive those simulations and provide user interfaces to them, perhaps even with front ends that simulate what those future observatories will see if they observed what was in the simulation, would be a great breakthrough and help people get ready for interpreting that.
So I think that it's interesting because we're all talking sort of about, ways to interpret data. I think that laboratory astrophysics is absolutely essential to really understanding the spectroscopy that we're going to start getting back on ices, on atmospheres, on dust, on grains, that sort of thing. And there's been a lot of work done in laboratory astrophysics that I think shows the utility of it. So in my area, there's a really nice pH database that you can actually take a look at laboratory astrophysics and simulation data and match it to your spectra. We're going to need more of that for more species of ice and dust and gas, because we're going to be able to see these very small variations in the physics of what's going on with them. And so to be able to understand them and interpret them, and to be able to figure out where's the interesting place to point, I think is going to be really essential.
I think for me, the big questions I'm most worried about for the future observatories are the ones related to the ways that our different science cases interact and might be coupled to different drivers for the facility and for the observatory. And so what we really want to focus on is finding ways we can simulate, kind of as Marc was saying, like what the future observations will look like, and also what they'll need in terms of potential future requirements, and how, like we heard about budgets this morning, can you sacrifice in one budget or one requirement to make something if you're doing really well somewhere else. Simulating as much of that on the front end is going to be helpful for the project. But what that requires us to do as scientists is have a really good understanding of the observations we want to do, and an ability to simulate and model them in an integrated way, where you push a button and you change one part of the observatory, and you see how it doesn't just impact the exoplanet science case, but the broad range of observations that the telescope has planned. That's not really an observation. The observations could certainly help inform that in the ways that you were hearing from other panelists.
Okay, thanks. Given the exciting science that we've talked about, which of the particular recommendations in terms of mission implementation were the ones which struck you as being the most relevant to the science that you're most interested in and that you would like to see accomplished over the next 10, 20, 30 years? I think I know what Suvi's going to say.
Mark, you haven't gone first yet. Do you want to go first?
All right, I'll go. Well, for me, the one thing I didn't say is I was also a member of the LUVOIR science definition team. So for me, that mission, and it's not just LUVOIR. I mean, I've been working on a concept like LUVOIR since 2006, I think. So I spent a good part of my career thinking about this. So for me, that mission is the one that I think I've tied my wagon to, and it's most relevant for a lot of the science. But with that, I will say a lot of the science I do requires both UV optical near IR, but also X-ray, because I study clusters, and they are the hot intracluster medium glows in X-rays, and there's a lot of real important physics you would miss if you didn't have those X-ray vision. So I think a mission like LINX is also extremely exciting. So if I had to pick number 1 and 2, LUVOIR and LINX.
I'm going to follow because I mean, obviously for me, it'd be LUVOIR, LUVEX, or HABEX as well. I will say though, like in a similar way, there's exoplanet habitability questions that LUVOIR won't be able to answer, right? It's designed to really look at the Earth-like planets around sun-like stars. There's a whole nother class of potential targets to look at, which are Earth-sized planets around M-type, smaller, redder stars. And LUVOIR is really not, neither LUVOIR nor HABEX were really studied to do that. That's something JW can start, but really origins and ground-based facilities would be able to pick up. Similarly, we really want to know through that, especially for the M-star case, how the star impacts the planet. And that's something that LINX would really help us understand as well. So like for me, and this is one of the things I really loved about the Decadal survey, is how thoughtful they were about mapping these big science questions, regardless of the discipline or subdiscipline, to a fleet of observatories, and thoughtful about how we could stack them together to understand things in a broader context. So if you're an early career, scientist out there, thank your local Decadal survey member, because they really did a great job with this one. And I think it's to the benefit of the future of the field.
And so along those lines, I really liked that, they set out, okay, we're going to do these flagship missions. They're big, they're bold, but we're going to do them because they're important to do. But I also like that they put in the probe line. And so we'll be doing probe missions either in the X-ray or in the mid and far infrared. And I think they both have extraordinary science cases. We heard a little bit from Marc about, X-rays, you can look at clusters and that sort of thing. With the infrared probe, you can look at galaxy formation way further back. You're talking about doing dust formation on these very, very small scales. And both of these missions are sort of the precursors for doing a flagship in their respective wavelength ranges. And so I think just the fact that there's a really nice pathway to not just do LUVOIR and HABEX, but also to do the next thing that's coming on the horizon. And it's really kind of the natural way that you would execute this, really a sort of storybook of doing all of the science. So that's very cool to me.
Yes, I was very excited about the recommendation for NASA to take a very deliberate and coordinated role in this revolution in time domain and multi-messenger astrophysics, and to have sort of a vision, a strategy of how to coordinate its existing facilities, and then think carefully about what sort of suite of instruments could support this dynamic field that's inherently across the electromagnetic spectrum, and then also needs to be in coordination with these ground-based facilities for gravitational waves and neutrinos. And so I like the idea of thinking broadly and having multiple missions, working strategically. And I think that's going to be really exciting to plan. And to help plan, I just wanted to mention that we're organizing, thanks to NASA is supporting a workshop to specifically answer the question of how should NASA support this vision for time domain and multi-messenger astrophysics for the next decade. and it's going to be in Annapolis, Maryland, not far from here, August 22nd through 24th. We're going to be having our first announcement soon and a webpage and everything, but please keep an eye on that. Eye out for that if you're interested in helping with the effort. Had to advertise.
All right, thanks for that plug, Suvi. So one of the things that, of course, factored indirectly into the Decadal survey, and if you remember, there was some discussion of delaying the Decadal survey because of the fact that we were awaiting the launch of James Webb. So we didn't do that. We have our result out. And so I'm wondering whether any of you have any thoughts about how Webb results might affect the science vision that has been portrayed in Decadal. What revolutions can we expect here over the next couple of years?
Well, so I was thinking a lot about that lately. I remember with the Hubble Deep Field, the thing that was so dramatic, that it taught us that there's a whole rich universe that exists in the first half of the age of the universe that we really didn't know existed. I think with Webb, there's going to be an equally exciting breakthrough in the first few 100 million years of the universe that Hubble just couldn't see. Ground-based telescopes just don't have the combination of resolution and sensitivity to see yet anyway. And Webb is up there priming to go. And I think in the next year, we're going to see things at redshift 15 and 20, and it's going to be mind-blowing. So I think that's going to then have a big impact on some of the science of those future flagships.
I think one thing that we're all going to have to get used to is that the things we're seeing in JWST images kind of in the background, they're not stars, they're galaxies. And it's absolutely mind-blowing to realize that, doing the basic calibration work, that sort of stuff, we're looking incredibly deep into the universe. I think that we don't know what questions JWST is going to make us ask. It will answer a lot of questions, but I think that there's going to be a whole slew of questions that we didn't even know there were questions. And I think that'll be exciting to see, how do we bring that into the development of these new, these flagship missions and that sort of thing. But I think the first thing is going to be, that sort of paradigm shift of looking at an image and realizing that we're seeing high redshift galaxies just right there.
I was going to say something really short, which is that just as an innocent bystander, I've been inspired, and I think the audience is inspired today by the success of JWST, and it sort of gives everyone the courage to do things that are difficult and challenging. And I think we're inspiring the next generation to go for it and think big and bold. At least I feel that way.
I mentioned the M-star case for JW. I think the other thing that would be worth mentioning is Roman and the chronograph instrument on board Roman, because we've already learned a ton about how do we do the starlight suppression required to take that little one pixel picture of a Earth-like planet or another star. That technology is super difficult, but Roman's really helped us. So I'm looking forward to see what happens with the rest of that project and to get its first images up on the screen of a planet directly imaged from space, exoplanet directly imaged from space.
Okay, thanks. One of the key lessons, we already talked about this briefly before, of the Decadal survey, one of the key emphasis was that science is inseparable from the people who do it. And so as we go forward with this great vision and the great science, how do you see us getting this message across to the next generation, and getting this message across these artificial boundaries that are there to involve the underrepresented groups and so forth?
So I was really glad to see the state of the profession incorporated into the decadal survey, because it is absolutely inseparable of the experience that people have and the science that they can do. And I think that it's a two-way street. It's not just how do we communicate to the underrepresented groups. It's also how do we change ourselves, because we really need to kind of take a look at what structures do we have, what rules do we have, what conventions do we have. Conventions not like this, but what default behaviors do we have that make it difficult or uncomfortable or impossible for people who are on the outside, who are interested in doing astrophysics and doing great science, who bring an incredibly important perspective, great ideas. How do we address those things within ourselves and within our community so that we can break those barriers down? Because we can't put that on people that are coming in to break down those barriers. We have to break them down ourselves. So I think that asking that question, whenever we do anything, whenever we implement a policy, a procedure, what are the unintended consequences? How will this be viewed by an underrepresented group? Does this assume knowledge of the community or of the processes that we have that not everybody might know? And so I think I'm really glad that the Decadal emphasized that. The appendices to the Decadal are absolutely fantastic. So if you have a chance, read through those as well, and they give a huge amount of perspective and really put a point on what the experience of underrepresented groups is in trying to get into physics and astronomy.
I think also, this has been said many times, is it really helps for underrepresented groups to see people that look like them in key leadership roles. So we have a bunch of new missions about to begin from ground zero. Let's pick put people that look like rest of the country and the world in charge of those projects, and that will go a long way.
One direction that I think is positive in our communities is this push towards open data access. And in particular, in the time domain world, we're kind of forced to do this because if you don't report your discoveries, you don't get credit for it in real time. So it kind of has forced the community to want to tell everyone what they're finding. But I'm hoping that with more of these large surveys, more of this idea of having cloud computing and access to compute next to data, that younger generations will only be limited by the creativity of their ideas and not their access to the data. So I think that's one really nice aspect of some of these bigger missions and bigger surveys, is this equal access to the data.
I think we heard this from Jane this morning, so I'm going to repeat some of the things that she said and give a big +1 to them. I think we have to be serious about ourselves as individuals and the systems that we're responsible for, the organizations that we lead, because when we're an order of magnitude of underrepresentation, that tells us that our systems are failing. Now, that doesn't mean they always have to fail. There's lots of examples of how we've combined funding and intention to make great strides in other areas. I mean, one is the technical stuff we do, but another is education, right? Like we've had amazing success by partnering between our technical experts and real education experts to spread the word of how awesome space is. And that happens throughout the world. We have intentional programs, intentionally funded, with people with domain expertise involved. And we need to do that, not just for education and not just for our technical work, but also for the DEI work. It needs to be funded, it needs to be tracked for success, and we need to bring in domain experts. We can't have scientists and engineers pretending to be the experts in these other areas. We need to bring them on as legitimate partners on these projects and in our organizations. That's what I'll take, in my opinion.
Thanks. So I have one last question, and then we'll ask for questions from the audience. And you guys can pass on this but I'm just wondering, having read the Decadal report, is there a science area that you felt was insufficiently emphasized there?
Well, I don't know if this was insufficient, but it's something we haven't talked about, and it was mentioned a few times, at least in the galaxies panel, which is micro arc-second astrometry. I think that's a fascinating thing. I mean, we talk about the pictures of Webb, which, you know, are way less resolved than micro arc-second. So from that perspective, the cosmos is mostly static. But when you get down to the ability to track things at micro arc-second levels, over the course of even years, you will see galaxies move. And I think, and that has all sorts of exciting implications for studying dark matter, studying the spheres of influences of supermassive black holes, a whole range of things. But it's an area that I'm not sure we've put our heads around yet, and it's a very exciting one, I think.
So for me, it's less a science area, which is usually where I'd start. It's more of a technology. Like if you rewind, before we started doing all these studies leading up to the Decadal survey, Paul Hertz, the APD director, had like a roadmap activity to say, like, what's the future of astrophysics? And the things that were kind of like next to make good on the next science cases for astrophysics were the things that went into the Decadal survey, and the Decadal survey said, yeah, those are good ideas, go and do them. But if you then look at like the generation after that, it's basically all interferometers. And we didn't have a lot of input on interferometry going into the Decadal because we were focused on those next things. But we can't just forget about interferometry, because eventually I think the science is going to call for it. And I think that's one thing I'm worried about in a very long time horizon, like after I'm retired and maybe my kids are retired. I don't know how long it's going to be before we get through these, but that's the one thing I'm worried about is interferometry. We need to find a way to keep that technology development going.
Okay. Before I move on to individual questions, I have a question to ask, but I need to understand if I'm the only one that's stupid. How many of you out here understand what we're talking about when we talk about astronomical decadal? So that's the majority. How many don't? Please, when this session is over, please meet Robert outside over here and let him to explain to you what it means. It's really significant. I just learned half an hour ago, well, maybe 45 minutes ago, but it's really significant, and it's some of the great things that we're doing. And he's one of the best people around here to explain it to you. So next, Abigail, do we have any questions online? Not yet. All right, so the questions, one new rule. You may ask a question of one person or of any people, but no questions for all. We have more space for folks. Who has the first question? Right there.
Okay, so that already disqualifies me, but I'll ask my question anyway. Okay. So it's more of a comment and dovetailing on what Marc and Shawn were talking about. I wanted to remind everybody that science is one, right? And let's not fall into the trap of compartmentalizing science areas, multi-messenger, time domain, planetary, exoplanets, and so on, because science is all one. And so if I put my strategic hat on, how do we keep the science areas that were not emphasized by the Decadal alive? In 10 years, we may have to do, we may be ripe for a CMB probe. And if we lose the abilities and the resources and the expertise in the next 10 years, we are not going to be able to propose for a probe, irrespective of the ground-based result. So I just wanted to remind the decision makers and the big bosses in the room who select proposals and do things like that, determine the course of astrophysics, I just wanted to remind them that, yes, the Decadal has spoken and has done its job, a wonderful job, by picking out specific areas. But let's not forget about the areas that were not mentioned, because we don't want to wait. We don't want to lose capabilities there. So,
Okay, thank you for your comment. Next question. Somebody else has a question. Back here.
As a communication person, I think we have a great opportunity to define what is the decadal review. So we just had the question, posed, and there are some people in the room that don't understand. So I think that, for people that are not familiar with this, maybe Rob, you could just give us a quick go-to. And then I have a very selfish question just of Shawn, because I do a lot of communication and people are obviously very excited about the idea of biosignatures. And hanging around in the astrophysics department at Goddard, near where I work, I hear a lot of, well, I don't think we can see this, and that's probably not possible. I hear a lot of the negatives about what Webb can't do. It's too low in the atmosphere. I'd like to hear from you what we honestly think we could see. So perhaps Rob could define decadal, and then I get my exoplanet question.
All right, I'll go first. So I'll keep this brief. Every 10 years, by congressional mandate, the astronomical community is required to do what's called a decadal survey. It's run by the National Academy of Sciences, so it covers all of astronomy and astrophysics in the US. And the goal of that report is to assess the status of astronomy and astrophysics in the US and set scientific priorities and make recommendations for the kinds of missions and programs that are needed to fulfill the science goals that are set by the group. I said it's done every 10 years. Usually a very distinguished group of panelists sits on what's called the steering committee. And then there are many, many other astronomers who sit on lower level committees that cover specific subject areas. And you've heard today from some of the people who have been on those panels, in particular, Rachel Austin was on the steering committee, and Patty Boyd up there and Jane Rigby were on the State of the Profession committee. And this is a multi-year exercise. This exercise typically takes 2 or 3 years. It started with input from the community. So the first step in this that happened 3 years ago was that the Academy asked for white papers from across the astronomy community on what they thought the key science problems were. They asked for what kind of mission concepts were out there. They asked for white papers about state of the profession issues. And all told, they got several hundred white papers that then this group had to wade through and use as input for the recommendations. So it's quite an involved process. And in the end, what comes out is the decadal survey report, which you can find online if you go to the National Academy of Sciences website. And in that is contained all the recommendations that we've been referring to and that the prior panel referred to, and I think the panels later on will also be talking about. But it essentially is the roadmap. It's essentially the marching orders for astrophysics in this country for the next decade. And so it's vitally important to everybody in the astronomy community. For those of us in NASA, it really is our marching orders, because NASA, and along with NSF and the DOE, are responsible for executing the things that are recommended in the decadal survey. So for me, as director of astrophysics at Goddard, I know what I'm doing the next 10 years because it's written down in that guidebook.
And there was a question for.
Yeah, so let me actually speak to the skepticism first, Michelle, and then come back to what I think we can do. I think the reason for the skepticism is because Webb wasn't designed to look for biosignatures. That wasn't the experiment it was designed to do. There wasn't an expectation it would be able to do it very well unless we were really good and really lucky. And about 5 years ago, we found out that we are lucky because we found the TRAPPIST system, which is a darn near perfect target for Webb to look at. And it's not the only one, but it's the first one where astronomers were like, whoa, we have a chance if we're really good. And now what we're learning over the course of the preceding weeks and months is the engineers and the program managers and the scientists that built Webb, they are good. and it's working great. And those two things together make it a possibility for some certain targets. Now, I'm like obligated as a theorist to tell you, like, I've got my concerns about the habitability of planets around M dwarfs because they've got this like high energy radiation that could irradiate the biology and much worse, like strip away the atmospheres in the ocean. So like, I'm not optimistic, but that's a theory. That's why we build these telescopes, is to test the theories. So I mean, whether that's right or wrong, like it's going to be cool to find out. And we should be able to do it for some kinds of life on some planets around certain star types with web. And it's going to be awesome, no matter what we find.
All right. One more question right here.
Hey, thanks. So, as an earth scientist, I'm, learning a lot and listening, but it makes me wonder about the opportunity for transdisciplinary science and transfer. So this is a question for Marc, since I had to pin somebody with it. So you mentioned about the simulators and, how it would be a breakthrough to have observation simulators. And we do that in earth science all the time. And we do observing system simulation experiments. Are there platforms where we can collaborate, like collaboration hubs, where we can share things that are in other science fields to advance astrophysics?
Well, I think that's a great idea, actually. I mean, in astronomy, we do have some simulators, but they're often tied to a specific telescope and not a general thing like, say, well, what happens if I double the aperture or add a new instrument or make the telescope twice as stable as it was in the pre. So we don't have that kind of flexibility right now. So if Earth science has figured out how to do that, yeah, we should absolutely. Maybe we should have a conference or a workshop on doing this.
Or a session in next year's Goddard. Yeah.
Yeah, so we've actually done some simulations using all the same platforms that the earth science folks do their climate modeling on to look at Proxima b, which is it's the nearest star to our sun, and basically, if you make some assumptions about what this planet looks like, you can put it into these climate models and come out with a planet. And it tells you all sorts of interesting things. It's tidally locked to its star. So that changes the thermodynamics of the planet's atmosphere and that sort of thing. So there are those collaborations, but absolutely understanding what that means now, taking that and putting it back into the simulations that Marc is talking about to say, hey, what kind of telescope would we build in order to figure out what the atmosphere of the planet is, closing that loop. But yeah, those collaborations are very, very fruitful, and we basically can use the same platforms that Earth science does. So it's great for multidisciplinary science.
All right, great. Robert, continue to do a great job. Thank you very much. I appreciate it.